tuning up some. Is actually tuning up a machine learning code that measures very precisely what the absorption lines are. So his undergrad was in engineering, and so he's got a lot of like coding background. And so we found a good sort of combination of the stuff he's already good at and the astronomy stuff that needs that skill. So he's working with a PhD student that I advise at ANU. And eventually they will be measuring the abundances of stars in 2 different streams in our galaxy. And so we think they're actually from the same original object. They were from the original galaxy, same original galaxy in the first place, but now physically they're a little bit separated in space. But to prove it, we want to go and measure like very precisely what are the abundances of all these stars. And so that's what, hopefully with the new and improved code that Wishek's working on, we can actually go and do that accurately. Yeah, and so the observing project we're doing tonight is actually on the Streams project. So we are looking at 2 dwarf galaxies that have not been captured by the Milky Way yet, that are very close by, and so we're measuring individual stars in those galaxies to see if they belong to the galaxy, or if they just happen to be kind of nearby in the sky, because that's really hard to tell without spectroscopic data. If we could find that they really do belong, then we could look at things like what is the kinematic pattern overall in the galaxy? Are they escaping? Are they sort of stable systems, or are they being pulled apart by the tidal forces of the Milky Way? And we can also look at compositions and stuff, look at age and metallicity and how those things relate in other galaxies. We have a decent idea in the Milky Way, but other galaxies have different rules, and galaxies at different masses have different rules. So we've got 2 galaxies, and then we've also got 2 stellar streams that we're interested in, where the questions there are, A, do these stars belong to these streams? Because again, you can sort of see an overdensity of stars in the sky that look like, you know, maybe there's a stream there, and you can look at proper motion, which is the motion of the stars across the sky, and if they're moving kind of together, then you go, oh, maybe they're really associated. But if you don't have the full 3-dimensional velocity, you don't really know. So we're getting radial velocities, and we're getting abundances, and we're just checking out, A, you know, what really belongs to the stream. But then when we have that, what can we infer about the population of stuff before it fell into the Milky Way? So this is a set of dwarf galaxies that just, they don't exist anymore because they've already been eaten by the Milky Way. And so if we want to understand what their evolutionary process was like, we have to go to these sort of fossils of them. We can't look at them live. We have to look at what's left after they fell in. So that's what we're doing tonight. And like I said, you're welcome to come up at 9, and Sherry will show you the secret way to the remote observing room. Dennis will also talk about astronomy, so I'm not the only astronomer. We do a lot of stuff. A lot of it involves galaxies. A lot of it involves stars. I mean, that's a lot of astronomy, right? Sorry. I mean, there's also exoplanets and radio and quasars and lots of other things that we don't particularly specialize in here. But anyway, yeah. Happy to talk to anybody about what we really do as astronomers, and I'm really glad you guys are putting this on. It's been a weird couple of years where we haven't really been able to do things with students, and so it's really nice to have, you know, feel a bit of activity there. So glad you guys are doing this. Thanks very much for having me.
Thank you very much. Really appreciate it. All right. Next up, we have the screen's going to work. It's on here, so I think that will have to do. One sec. Bear with me, it's me. I think we're just going to push ahead. Yeah. All unfortunately, I don't know if our recording is going to have these, but we will push ahead anyway. All right. Yeah, please welcome Dr. Scott Lyles.
Okay, thanks. Thanks, everyone. Just can I point at things? Anyway, it doesn't matter. I can just point there, right? All right. Hey, I'm Scott Lyles. Thanks for having me. Thanks to PhySoc for organizing this. I should check. Can I change my slides? That's good. So yeah, I'm Scott Lyles. I'm from the Quantum Electronic Devices group. I'm here also with Matt Rendell, who's going to talk in a little bit. And we're both postdocs in the group of Alex Hamilton. And our group has, I think, 7 postdocs, 5 PhD students, and an honors student. So we're a reasonably big group, which is good for students. We're primarily an experimental group. Can I find it? Oh, there we go. Let's see, what have I got? Laser pointer, beautiful. So we're primarily an experimental group. Basically, quantum electronic devices means we study electronic devices that operate based on quantum physics. This is an example of a quantum electronic device that we've been measuring. The measurements we do are usually with cryogenic temperatures. So here we have some of our group members assembling a dilution fridge. Here we have one of our group members, Daisy, doing everything all at once. We also so the dilution fridges cool our samples to 10 millikelvin. If we want to go less cold, we also have liquid helium, which cools our samples to 4 Kelvin. And then we also, we run the experiments through the computer, obviously. So as we've got quite a few team members, we have quite a few groups, quite a few projects going together. I'm going to talk about the whole spin 3½ qubits. Matt will talk about artificial quantum matter. But we also have projects on nanowires, which are one-dimensional wires that allow electrons to basically travel through a quantum wire. And then we also have projects Alex has projects looking at the hydrodynamics of electric current, which was interesting because they found that in some devices, the electrons are extremely viscous, almost as viscous as honey, which is not quite what you would expect. We also have a nice social aspect to our group. So here's an image of Karina setting up a very complicated whiskey tasting experiment for us. All right, so yeah, as I said, anyway, I'm going to talk about whole spins. This says artificial quantum matter, and then Matt Rendell, and then we'll do a summary of how you can get involved if you're interested in any of these things. So before I talk about whole spin qubits, I should just quickly cover what is a qubit. So a qubit is a 2-level quantum system. You can represent a qubit basically thinking of it as some state, which is the linear addition of 2 quantum states, sort of psi1 and psi0. And this is useful for quantum computing because you can think of this in terms of bits, like classical bits, you have your 1 and your 0. However, for qubits or quantum bits, the state can be thought of a vector, which can point anywhere in this sphere. So it isn't confined to just being 1 and 0. And this lets you do different different information processing than regular classical allows. A big question right now is how would you actually make a qubit? And there's quite a few different approaches. The approach that I'm talking about today is called spin qubits, which is actually quite a nice system because it's quite intuitive. You use this up and down spin states of a single electron as your 1 and 0 states for your qubit. This also has the nice advantage that it can be implemented in semiconductor technology. And you don't have to make too many changes to the existing billion-dollar silicon foundry to actually start making spin qubit type devices, which is quite nice. In terms of like the ingredients you would need to make a spin qubit, the first thing you need is a confinement. So just think of your second-year harmonic confinement. You've got a nice confinement which can trap a single electron, or for us, a hole. You then apply a magnetic field. This splits the spin states in energy by the Zeeman energy, which is given by G mu B. And then you also need to understand this state quite well, which is where our group comes in. We've been studying the spin properties here. And these are mostly captured in this G factor. So If this equation is familiar, just keep track of G because it will come back to it. That has nothing. What have I done? I think I went to the end. Hey, that's my slide.
Yes, spoilers.
Yeah, so I'm going to talk about Okay, cool. All right, so before I talk about hole spin qubits, obvious question, why bother with holes? Why not just electrons? What makes holes interesting? And the thing I want to take I want you to know is holes are not just positively charged electrons. And the reason that's the case is if we look at a sort of generic semiconductor band structure, electrons occupy this conduction band, which is S-like and has L equal to 0, angular momentum 0. Holes occupy the valence band and have L equal to 1, which is a p-like orbital. And since the spin orbit coupling in semiconductors goes as L dot S, this means that holes having a non-zero L will have a large spin orbit coupling. Now, and one other aspect is that holes also have a total angular momentum of 3½ since it's L plus the fermionic spin, which means they have a different spin property to what you might expect for spin half electrons. If all of that was a bit too quick, I did do it too quick and too generic. The main thing I want you to understand is that spin qubits made with holes are expected to have very different properties to spin qubits made with electrons. And hole spin qubits are not very well studied, and that's what we're looking at here in our group. All right, so the first ingredient was actually confining a single charge. So this here is a scanning electron microscope image with false colors of the actual device we use. Again, it's a pretty picture with lots of colors. But actually understanding how the device works is not too complicated. So on the right in blue, we have a reservoir of holes. We have a tunnel barrier and then a confinement potential, which is defined by just the voltages that you apply to these gates. On the left in green, on this side in green, we have a detector, which basically just detects how many holes are trapped in this confinement. To begin with, you have some sort of confinement potential. It's got discrete energy levels. And then you have the reservoir here, and the energy is lower than the confinement, so you have no holes trapped. You adjust the voltages on one of the gates to cool the bottom of that well down. And at a certain point, you're able to load one hole into the dot. And we see that as a spike in our sensor signal. And then we just keep pulling the voltage down, and we can load, in this case, more than 8 holes, and we can see them sequentially being occupied. For the actual spin qubit, we said we want to have just one hole, since we want to just split its states. So now we know we just go to this position and we have one trapped hole. In order to really know that this is what we were measuring, we had some collaboration with some theorists who produced some simulations of the device. They were able to simulate the whole probability density for our device, and it showed up as we expected with a nice single hole confined in a potential under one of our gates. So with this single hole, we want to study the spin properties. As I said, the spin properties are pretty much captured in our G tensor, in our G factor. And so what we can look at is just the splitting of the up and down spin states as a function of field. We do that for a couple of different device parameters, and from the slope of each of these lines, which are basically just the increasing splitting here, we can extract a range of different G factors. And the interesting thing here is our G factor is not actually constant, which is more or less what you expect for electrons, but we actually have quite a large range of control of our G factor, which means our device parameters are really affecting the properties of the spin here. And we looked at why this is the case, and we found that when we simulate the different device parameters, what we're actually doing is pushing the wave function across, and the spin properties are actually very sensitive to where the whole wave function is in this device. And just to point out, this is only a 10 nanometer shift, and we're seeing a over 100% change in the G factor. Let's skip that one. So the final thing, we've trapped a hole, we've studied the G factor. I promised a qubit. So for those of you who are experts, I'm doing a single triplet qubit, not a single spin qubit. For those who don't know what that means, great. But the point is, we have measurements of the probability of being in the 0 or 1 qubit state. And as we vary the operation time, we see nice oscillations between those two states. We know that the frequency of these oscillations depends on the G factor and the magnitude of the field that we apply, the magnetic field. So we increase the field and we see the frequency of the oscillations increase. And then we increase it even more. We see the frequency increase even more. Here it looks like dots, and I've just hopefully fit a sign to it. But if you zoom in, you can see the blue measurement dots do actually follow a sign pattern. But what you can see is that now the amplitude of the oscillations are dying off rather quickly. And so that brings us to the conclusion of where we're at. Pretty much what I'm going to be looking at on Monday is we've demonstrated the spin qubit, but we still have some work to go to improve this. Particularly, we want to look at this decrease in the amplitude because that's to do with our qubit operation. And the approach is we've been working with Dimi Kolsa's group to look at some theory to understand these systems. So that's the end of my spin qubit stuff. Matt's going to talk about the artificial quantum matter. Thanks, Matt.
Hi everyone. Yeah, thanks Scott. I'm Matt. I'm another postdoc in the group, and I've just started working on this project, which is quite a new one, where we're engineering artificial quantum matter in our quantum electronics devices. So some of you have probably already studied or looked at this in solid state physics already, but a lot of solids, especially when they're crystals, get many of their properties from the way that atoms are arranged in the solid. And so you can see an example here of a graphene lattice, which is a one-dimensional hexagonal lattice. And this is the band structure that is produced by this lattice. So this lattice comes from the arrangement of the atoms, right? So the varying electrical potential. But there's no reason that this has to come from atoms, right? You could create this in a bunch of different ways. And so our technique for making this varying potential is by using electrical gates. So what we have here is we have like a nice little very thin stack of electrical gates. So we have a gate up here, which we use to create this modulated potential, which is separated from a second gate, which we've just punched a bunch of holes in using an electron microscope. And so what we're able to do with this is we're able to create an artificial version of this atomic lattice purely by applying voltages to these gates. And because these metal gates are things that we can create in the lab, like we can create the size of the gates, we can create the size of the holes, we can change the spacing between the holes, we can essentially impose this, this lattice on top of any material that we want. So in our group, we're doing this for two things. So the picture here shows a schematic of a 2D electron gas inside a semiconductor. So this is a two-dimensional layer of electrons confined in a stack of different semiconductor materials. And the other thing we're working on is doing this on top of a layer of graphene. So you're starting with this graphene potential and then applying a second potential on top of it. So why might you be interested in this? Well, if you're looking at an atomic lattice that already exists, this is the way the atoms are, right? And this is the band structure you end up with, and that's it, right? If you want to change it, you need to use different atoms or use a different crystal. Because we're using metal gates here, you can change the voltage, and this changes the modulation potential that you're applying to your electrons. So there's a little schematic here. So you can see if this is your chemical potential here, and this is your modulation that you're applying, just by changing the voltage, you could change it from something like this to something like this. So we can really get a feel for what this potential is actually doing to our 2D system. And I guess the other advantage of this is, there's no real limit to any of the kind of patterns that you can create. So here's a bunch of examples of different patterns that we've created in the lab. And so, you're not limited to any sort of crystal structure that you can create with a semiconductor. You're kind of limited by how small you can pattern, and the time of us to actually do the patterning. So we've seen some interesting kind of results from this already. So we can make a bunch of lattices with a bunch of different shapes. We've already demonstrated that you can essentially use these lattices, and by changing the modulation, you can make your electron look like it's changed sign. So it travels the opposite direction in a magnetic field to what you would expect it would. And also, we've seen some signs that you can essentially make the electron behave like it has no mass as well. And so some potential other things we could do are look at different types of band structures, potentially observe superconductivity. So this is kind of a new project that's just starting, and it's looking pretty interesting so far. Yeah, that's the same diagram again. Okay, so some other things that we're working on in the group. So that's kind of my focus and Scott's focus, but there's a few other postdocs in the group. So one thing that we're working on is making a transistor out of a single crystal. So normally when you're making a transistor, so this image here is called a transmission electron microscope image. And so the way this works is by shining electron beam through a crystal. And so every little dot that you can see in the picture here is an atom, right? And so this is showing you the real clear, like, crystal periodic lattice of the semiconductor. And then typically what you would do is you would, you know, grow your beautiful, nice crystal, and then you take it out, take it into the lab, run a bunch of other stuff on top of it. But then you end up with like a bunch of gunk on the surface. Whereas what we've started doing is instead you grow a layer of metal inside your vacuum chamber on top of your semiconductor crystal that already exists. And so essentially this layer between your metal gate where you apply your voltage and your crystal never gets exposed to air. And so this makes them behave significantly better, like an order of magnitude better than a typical semiconductor transistor. And so we've also been able to pattern these into nanostructures and observe quantum effects. So you can see these little steps here are changing the width of a 1D channel by 1 electron at a time. That's these little quantized steps. Another thing that the group works on is quantum wires in holes. And so this is constricting your 2D hole system into a single dimension. So you only have holes traveling in one direction. And then using this to study the electrical and magnetic properties of your crystal just along a single direction. So you can imagine if you have your crystal structure, you know, your crystals are arranged in a certain direction. If you measure along different directions, you see different atoms as you go along that direction. So that will affect your electrical and magnetic properties. And something else we're looking at is hydrodynamics, which Scott mentioned briefly earlier, which is where you're basically changing the viscosity of your electron fluid as it flows through your semiconductor. And you see all sorts of interesting hydrodynamic effects from that. So what this little schematic is showing here is, you know, normally you'd expect your electrons to just flow straight along your channel like this. But if we add these little like crenellations to the edge, what ends up happening is we get little eddies forming in the flow of the electrons as they flow through. And you can observe this in changes to the resistance of your electrons as they travel to your crystal. Yeah, so I guess what kind of things will you do when you're in the group? So you'll get hands-on experience with quantum devices. You get to play around in the lab with cryogenic equipment and electrical equipment. You'll also learn a lot of how to do AC circuit design, a lot of programming, and if you're lucky, especially if you're doing a PhD, you'll get to do some hands-on time in the clean room, like I think this is Alex here, back when he was a lot younger, learning how to make these samples as well. And yeah, if you're interested, feel free to contact Alex or Scott or me. If you're interested in me and Scott's projects, you can contact us directly, or if you're interested in the other projects, let us know and we can get you in contact with some of the other postdocs. And these are all the kind of things we offer in the group. So we have summer students, people doing taste of research, and then honours and PhD as well. Scott, do you want to add anything else? No? Cool. All right. Thank you all for having us.
Thank you very much. We'll also, these slides will get uploaded, so you can get these details. Otherwise, feel free to approach me or, you know, anyone in the school, and they can point you towards the right direction. Next up, we have Professor Dennis Stello. Yes, we might just see if we can get.
Okay, so I will take you through a little of a roller coaster ride through what has been happening in part of astrophysics. So I call it the astroseismic revolution. So I work in astroseismology, and the word basically means streamers of stars. So that's what we do. And we do that both to learn something about the Milky Way and those things around stars, known as planets. And of course, the stars themselves. That's interesting fundamental physics to do that. So just a short introduction to astroseismology. Just a quick show of hands, who knows what an HI diagram is? Okay, that is most people. That's basically our periodic table for the astronomer, right? You take all the stars from the sky and you plug in their color or temperature versus the luminosity. And they fall in this particular band. And it basically shows you where the star is in its evolution, and it also shows you something about its mass. Now, all the stars, most of the stars in the sky, they live on this part here, the cool part where the sun is. And they all have in common that the envelope, so not the core, but the envelope of it is connected. So it's basically like boiling gas. And so from that boiling gas, we can learn something interesting, which seismology takes advantage of, that enables us to peer through the surface and look inside the star. Whereas all the classical measurements from astronomy just see the surface properties. In fact, this diagram is based on surface properties only, temperature and luminosity. And the spectra that Sarah was talking about is also surface properties. It is about what is right at the surface of the star. And so our knowledge until seismology really started to revolutionize was based on knowledge about fundamental physics that we know from the lab. Then we can build a star in the computer, and then we can constrain it from its surface observation, and then hope that all the interior stuff is right. But seismology is the only way you can really test it. So, how it works, this is a cartoon of the sun. So they have convection near the surface. If you take a little pixel of the sun and you zoom in, this is actually what you see. So you see this granulation pattern, which is resembling hot gas coming from below. That's the brighter stuff, and the darker stuff falls back down. That's the convectional process. The cells of these granulation bubbles are roughly the size of states. Okay? That's supposed to be a simulation. It's not. It's a boring one. So if you want to see convection in real life, go to a Japanese restaurant and order miso soup, because their turnover time scale is about a few seconds. So you can actually see the granulation cells, and you can see the miso kind of follow that pattern. It's exactly the same thing, but it has to be hot. Otherwise, it won't show convection. So if it doesn't, turn it back and say it's not hot enough. Okay. So this very vigorous gas motion at the surface hits the star. So these bubbles of gas reach close to the sound speed, the local sound speed of the star when they hit the star from the inside. And that basically sets up sound waves to start make the entire star ring, like a big bell. Okay? It's like picking a big gong in a sandstorm where grains of sand randomly hit on the gong and it will start to ring in this natural mode. That's what these oscillation cells do. And the standing waves that get created by that can be described by these kind of guys here, and those of you who have done quantum mechanics would recognize them as these functions we use to describe atoms as well. These are spherical harmonics. So that's actually what the sun is doing all the time, and all the stars, most of the stars you see in the sky. Obviously not with these high amplitudes. But we can measure it in different ways. We can either measure the actual physical movement, so the radial velocity shift of the surface coming towards you and going away from you. We can measure that from spectra. Or we can measure the brightness variation associated with it, because the gas is expanding, therefore cooling and compressing, and therefore getting hotter. And so the whole luminosity changes. And so you can measure either of those, and it gives you a frequency of oscillation that is the frequency of the sound wave ringing inside the star, making that thing happening. So you get the frequency. not by listening to the star, because you can't, but you can see what is happening on the surface from the ringing inside the star. So we get all these nice frequencies for all these different modes. They are very hard to measure. The solar surface walks along with walking speed as it oscillates. Okay, it's very slow, but we can do that. And the brightness variation is only a few parts per million, so it's tiny. We can't do that from the ground because the Earth's atmosphere is basically twinkling starlight too much, but from space, it's brilliant. So, from these frequencies, we essentially measure what the sound speed is in the star, because as the sound speed changes in the star, its frequencies will change. Just like if I inhale helium, my voice will change because the sound speed will change in my throat. I didn't bring that demo. And that gives us therefore information about the interior structure, because as interior structure is changing, therefore the sound speed and therefore the frequency we measure. That's how it works. So the revolution really started with Kepler, not the guy, but the satellite. It launched now 15 years ago, something like that. And that is an image of what the Kepler field looked like. Zooming in, these are all the stars in the Kepler field, and we were measuring hundreds of thousands of stars. We were simply just measuring how much light falls on the pixels for each star. And we did that every half hour, okay? That builds up a light curve that Kepler was supposed to look at and figure out which of them had dips in them because there were planets around the stars. We don't care so much about the planets. They're just annoying dips in the light curves that we remove, but the residual is really interesting because that shows oscillations. So this is the ringing of sound inside the star that is revealed through its change in luminosity. And so that's actually helping us to also figure a bit more out about the planets. So the planet people were really happy that we wanted to play with their Kepler data, so we got it for free. So the way we do it is we take these light curves of variation. They look very complicated, but that's because there are many modes of oscillation with all different frequencies oscillating at the same time. So what we do, we decompose it into sine wave components, which is called a Fourier transform. And therefore we can see this nice picket fence. Each peak represents a sine wave hidden in that signal with that frequency and that amplitude. So all these added up gives this stuff, okay? If we zoom in, we can see there is this nice pattern in the picket fence that repeats itself every now and then. I've indicated here some numbers. They're just the type of modes that are causing them. So the ones with 0 are just purely radial modes, breathing in and out. In quantum physics, you would call it L equals 0. The guy sitting next to it is a quadrupole mode, L equal 2. And that one halfway in between the pairs of 0, 2 is the dipole, L equal 1, okay? And that's the octapole sitting there. Now, what can we actually learn from studying these frequencies? Now, as we know, when we go to the symphony, we can have instruments that look very similar, but they make very different frequencies. And obviously, in this case here, size really matters. So size is something that reveals what the object is in terms of its frequencies produced. So this is an example where we are doing that from some early Kepler data. This is again the HI diagram, if you like. Some stars. These are not so evolved stars. These are very highly evolved stars. So they are big stars. This is the light curve from Kepler from just 4 examples. And you can see the number of wiggles or brightenings and dimmings is about the same in all 4. But the top one takes 10 times as long to do it than the bottom one. So which one is the biggest star? The top one, yeah. It has a deeper voice. So if you actually analyze the frequencies and figure out the size based on the period of these wiggles, these are the actual relative sizes relative to the sun that we got from that data. Now, and if that had played ball, I could have shown you what a sound file would look like if you converted these frequencies into sound and multiplied by 1,000,000 to make it audible, but that will be for another day. But there are more things we can do. We can simply look at this envelope and go, well, where does it peak? It peaks somewhere in the middle, and that is sensitive to the surface gravity and its temperature. And the spacing in frequency where the pattern repeats is a very accurate measure of the mean density of the star. And this spacing here between the radial and the quadrupole is a measure of its age. And age is notoriously difficult to measure for stars, unless it's the sun, because we have meteorites where we can age data. We can't do it for distant stars. And this is the only method that really measures what is happening inside the core of the star, which is a measure of how old it is. So the way it works is that the radial mode, so L equals 0, travels through the core. It feels when hydrogen turns into helium, because that changes the sound speed in the core. The star is sounding more like Mickey Mouse, like it's inhaling a helium balloon. But that's only that mode that changes due to that. The quadrupole only lives in the envelope. It doesn't feel that. So the relative frequency between those two gives you essentially how much hydrogen has turned into helium in the core, therefore how old the star is. Now we can do more than that. So here again, I'm showing some Fourier transform of two different stars in this case, and you have this picket fence of peaks. The ones I've indicated in blue are the ones that are nicely equally spaced and tells me the mean density. So they're about the same, about 8 microhertz in spacing. That basically means that these stars in the HI diagram sit roughly at the same point here, where they are red giants. The problem is, for those stars, they look very similar from outside. The surface of them you can't tell apart. So in this diagram, they fall right on top of each other. So we don't know whether they are on the way up in the evolution or on the way back down, even though that's very different evolutionary periods. But there's some of these modes that behave very different between these two stars. These ones have some small spacings, these have some very big spacings. And that's because these ones are very sensitive to what happens right at the core. And that one of the stars have a core that has expanded because helium has started to burn, the one that has come down, whereas this one hasn't started to burn in the core. It's basically an inert core. So we can clearly see the difference in where stars are in their evolution, because we can look inside. Another thing we can do is we can look for rotation. And again, if you've done quantum mechanics and know about what happens when you put a magnetic field on an atom, you can have splittings of the modes. You can get something that is normally degenerate. You can get non-degeneracy there. So we have here in dots, I indicate where I would normally find one peak, one oscillation mode happening, but I see 3. So that's because we have dipole modes there, and for dipoles, they come in 3 flavors, m equal -1, 0, and +1. And when the star is rotating, they are not degenerate, those frequencies, they split up. And the amount they split up tells me how fast the star is rotating, where those modes spend most of their time. This mode spends most of the time in this other part. So it doesn't rotate that fast out there. This mode lives a bit further in. It's split more. This one is split even more. It lives very close to the core. So we get a differential rotation of the star. And doing that with stars at different evolutionary phases as they become bigger, we can basically figure out that we are missing physics. Is that a question?
What's really splitting over there? Right.
What is splitting?
Yeah.
I will show you an animation that shows that. I hope I didn't remove that.
Is it okay if I ask a question?
Yeah.
I don't know if it's but like you know how like in air there's like only one kind of sound wave, but in like solids like around there like 2 types, like in earthquakes, and one moves faster than the other.
Yes.
Is that the case in stars?
Also, yes. So here we have both pressure waves P modes and we have gravity waves G modes, and they couple to each other, and they live in different parts of the star.
Don't they have like produce different like standing waves? Because one moves faster than the other. So like
I mean, the modes themselves are excited here, and they start out as being pressure waves. But the G modes in the core that live here, they just get energy from the P modes because they couple. It's basically like coupled oscillators. So we figured out by this that there was a missing physics in our models about how rotation occurs in stars. And that is simply transport of angular momentum. We don't understand, because it's very complicated when you have hydrodynamics in these complicated blobs of gas. Now, we can do even more Like magnetic fields, the thing we usually put under the carpet because it's too hard, but now we can't anymore. So up here, I again show these picket fences of 3 normal stars. This is just the way evolution goes. This is least evolved. This is most evolved in those 3. And I've color-coded the peaks according to which sort of mode is causing the peak. For each of those 3 normal stars, I could find these kind of not so normal stars. They are otherwise indistinguishable from the normal ones, same surface properties, and even the same frequencies, except there's hardly any power in the dipole modes. And that missing power turned out to be strong magnetic fields in the cores of these stars that were generated when the stars were on the main sequence, in the main part of their life. And that generated magnetic field has been frozen in until the star has become a red giant, where we now see it is affecting the oscillations. And so we basically can measure the presence of magnetic fields because they are sucking energy out of those oscillations. Okay, so why should you care about this revolution? Because it really is a revolution. This is how many stars we could play with before all the space missions started. 1 space mission, 2 space missions, and now this number is 200,000 with TESS, which is currently flying. So we have lots of data and big opportunity to learn a little bit more about this thing here that Sarah also cares about. So we know a lot of what happened in our neighborhood, but if we go further away, we know much less because it's hard to measure properties of stars. But with seismology, we can do it very accurately, and now we can actually do it quite far away. Look at Kepler, it goes like several kiloparsecs away. And so these are the first missions, so they were kind of beams, but TESS is now full sky. And so we basically have a full sky mission currently running, and the machine can run for at least a decade, and it has certainly worked fine so far. And just from the first 2 years of its mission, we found 200,000 stars oscillating just like that. Okay. One of the problems with all this data, it's kind of a luxury problem, is that we were used to having such a person called an expert sitting and vetting results from otherwise automatic pipelines because they make mistakes, whereas experts don't. But what we figured out was, and this was kind of the time where image recognition and AI really started to get its way into different research fields, and we figured out we could use it. So we have started here at UNSW to really promote that use of AI to basically take over the task of this vetting. By basically learning or training the network to do or look for similar things that the expert would look at. And to our surprise, what the AI methods actually are looking at in images are very similar to what the expert is looking at in order to make the decisions. So it gives us a bit of hope that it actually does the right thing, and obviously we can quantify that it does. Then there is more missions coming. This is a European one, but I will just list some of the others. So K2, Kepler, and Kourou, they are all done, but there are still this today. Kepler was finished like 10 years ago. But we are still publishing more papers per day from Kepler data than when Kepler was flying. And so that's also the case for K2, and TESS is still ongoing. So these ones are coming, and we are looking forward to that. So if you will be working on astroseismology, that's your playground. And I'm happy to take questions. Thank you.
So the vibrations in the core are caused by the elemental changes, right? Like new elements are formed, and that's what causes these waves, right?
The waves are not caused by the change.
It's an after effect.
The waves come from the surface. It's from the convection at the surface. That's where the energy comes from for the standing wave. And the waves are simply just sensing what is the physics in the star as they travel through the star.
So can a similar phenomenon be observed in like any other type of astronomical object, like instead of stars?
Yeah, you can see it in the Milky Way. The Milky Way is wobbling. So that's seismology. Because when there's a kind of a smaller galaxy kind of bumping into the Milky Way, you get wobbles of that whole plane because that's just a gravitational plate. And if you disturb that, you start to see oscillations. And you have a thing actually called galactic seismology now, because with the new missions from Gaia, for example, we can start to see how stars are wobbling around.
Well, you also talked about how how elements, when they change, like from hydrogen, helium is being formed in the core.
Yep.
How that is, what is that affecting them?
That is affecting the sound speed and therefore the frequencies of the sound wave. Because as they travel through the star, if they suddenly feel a different sound speed, then they will travel with a different speed, and therefore the frequency they set up as a standing wave will be affected.
And can such a phenomenon be observed somewhere else except for in stars?
If I inhale helium, yep.
Can it happen in the planets? Like you're not.
Yeah, so people have tried to do it on Jupiter to figure out whether they could find oscillations in Jupiter. But it's hard.
Okay, because maybe if there is a change, it's like too subtle to notice.
Yeah, but it's also because you need a source to generate the frequencies to an amplitude that you can measure. And you need enough light to get a signal to noise that's high enough. And that's tough with planets because they don't shine.
Can you measure it by maybe trying to measure the core physically, like by touching and drilling through the core and drilling through the core and measuring it through the crust. And then,
In principle, but in practice, I would say no.
Yeah, in practice, no, but will it work for planets?
Huh?
Would it work?
Would it work in principle? I would say yes, but in practice, no. Yeah, what's that question?
How big is your model, the training model?
The what model?
The training model.
Oh, that depends on the application. It can be anything from, tens of thousands.
Okay, well, I guess what I'm asking is, you're using real data to train your neural network.
Both.
Simulation.
Both. Yeah, depends on the application. But usually we would use real data.
And how big is that data? And how many stars have been identified?
So we are now at 200,000
100,000 have been positively
found to oscillate. Yeah. Yeah.
Are there any cases where they haven't been oscillating?
Other cases where what?
It hasn't been oscillating.
Hasn't.
Yeah.
Not plenty. I mean, mostly the case of non-oscillations is just because our detection limit is too bad for it, simply.
Yeah.
I mean, the better you can measure. I mean, all stars are oscillating at some level. So currently, what I've showed you is mostly red giants, because bigger stars oscillate with a larger amplitude, and that's easier to measure. So to measure stars like the sun, we can do that, but then it's much fewer of them because they need to be nearby to be bright enough for us to have high enough signal.
Can you measure oscillations if they're two stars or neutron stars that are moving really fast close to each other? Would that be interesting?
Maybe, but these kind of oscillations you don't see in neutron stars. But I mean, obviously you see gravitational waves from them. That's a different type of waves, but that's one of the things we don't do at UNSW, actually. Although we do many things. Yep.
Which engine are you using for your neural network?
Whatever is out there, in the Python world of packages. We don't,
there are quite a few.
Sure, but we haven't limited to any specific ones. Yep.
So if you use this to measure lots of different properties of stars, how do those measurements in this compare to other methods? So, like looking at the star of the size, for example.
So I don't think I have a plot of that. It obviously depends on which property you're talking about. If you want the temperature of a star, the surface temperature, you would use a spectrum. You wouldn't use seismology for that. If you wanted surface gravity, you would use seismology for that because it's an order of magnitude better than from a spectrum. If you want its age, you want to use seismology because anything else would be much more model dependent. So it depends on the use. The thing that is good about astroseismology is the precision doesn't depend on how far the star is away. As soon as you have the signal, as soon as you see those peak above your noise level, you have the measurement, and it is as precise as you know the frequencies, which is just determined by how long you have observed. Whereas typically, if you say observe the distance of a star in a classical way from parallax measurements, it gets worse by the distance. But I can get a parallax for stars for astroseismology out here, like 20 kiloparsecs. There's no other mission that can go anywhere near that. Yeah, it's all down here, close to where we live. But that's because of that fact. As soon as the detection is there, there's no change in. I mean, it's just a matter of getting photons to get your detection, and then you're fine. Yep.
First of all, just want to say that this is really crazy. It is mind-blowing crazy that this was thought up. I think I missed most of the talk, and so I'm more curious about when was this first floated as an idea? So I can't imagine coming up with astroseismology.
When what?
When was like the whole idea of astroseismology floated?
So it started out in the 60s, where theoreticians were predicting that these oscillations should exist in the sun. And so people went out and observed, and they indeed find a hump of excess power around where it was predicted. And so the field of helioseismology got born around the 60s. And then around mid-80s, people started to think about maybe we should start to do it on other stars. But it took a long time, and that's because those amplitudes of the oscillation are so tiny. So people tried both with photometry, so the brightness measurement, but was not successful from ground because the atmosphere is just twinkling starlight way too much. And then radio velocity was also hard back in the 80s because we couldn't even detect planets back then, right? But then the planet people, they also needed high radio velocity precision. And then when you say planet, dollars start to flow. And then machines get built and we piggyback. And that happened with photometry as well, because then the planet people said, well, if we really want another planet, we need to go to space because we can't do radio velocity measurements of a lot of stars. We can only do photometry of a lot of stars because we can take pictures of the whole star. And then they made really good photometers that got good at measuring photons. And then we piggybacked on them. That's how it worked. Okay, I think my time is over. So I will give the floor to the next speaker.
No, we can take this one. Yes, and then I'll get ready to sit up.
Yeah. All right. Cool. So we're running a bit ahead of schedule, so we're going to take.
Okay, well, thank you for staying for the second half of the academic. My name is Maya Cassidy. I'm a new academic here in the School of Physics, and my work is in the area of quantum computing. I'm going to give you a talk today, not just about my own personal research. I spent a lot of time in the industry, so I actually can't talk about what research I did, but more like a high-level picture of the quantum computing industry. And where's your quantum computer? Where's my quantum computer? Why's it taking so long? What's going on? So I'll start with a bit of a background about myself. So I was actually a student here a very long time ago in electrical engineering, and went into electrical engineering kind of because I didn't really know what else to do. I was like many of you, good at maths, physics. I heard that engineers got jobs, seemed like a good option. And I went through and did my courses. I never, in my, say, 3 years of my bachelor degree, I never went into any lab apart from like what was absolutely minimum required, and as part of the coursework and enrollment. And then I had to do honors, and I signed up to do it at CQCT, and I went to the dark side, to physics, and I totally loved it. Like I absolutely, like I had this whole world opened up of experiments where it wasn't just coming in and like following some manual of like press this, do that. Like you had to build the thing, you had to create the thing. It had to be like something you could imagine, and then you built it, and then it worked sometimes. And so then I was hooked, and then I became I transitioned from being an electrical engineer into being a physicist without having really ever taken any physics courses. I then decided I really wanted to be a physicist, and so I went to graduate school in Harvard in the US and did a PhD in physics there. And I did research actually in sort of the intersection. So I was doing undergraduate research at CQCT in spin qubits at the time. A lot of, and that has continued on over the last 20 years. I went to Harvard and I worked on actually applying some of these techniques that we use for qubits to medical imaging and trying to build better sensors to track disease and image what's going on inside the human body. We spun out a company out of that, and I kind of got an itching to get back into real physics from that technology. I did, at that time, quantum computing, when I went to do a postdoc, quantum computing was sort of at this really interesting phase in its evolution, where it was starting to break out of the academic research lab. Like it was starting to be clear that there was going to be an industry there. And I thought, okay, I want to be part of this industry. So I went to TU Delft for a postdoc, worked with Leo Kahnhoven, who is one of the founders of the fields of spin qubits, spin-orbit qubits. I was working on topological qubits there. And we had a number of industry partners come knocking on our door. And one of those was Microsoft. And they basically came and hired us all. In that complex negotiation, I said, hey, I'm Australian, I really want to be back in Sydney. Luckily, there were some other people that Microsoft was interested in at the University of Sydney. So they started up a lab there based on us. And I was there for 6 years, working on how do you actually build a quantum computer? And why don't we have one yet? And why is it so hard? And so now I'm back at UNSW, and I'm really loving being here with all of you. I love the energy out of working with students, and I'm still working on why don't we have a quantum computer, but approaching it from a slightly different angle. Instead of sort of a big company picture, and throw massive resources at problems, think about it in a creative way. What are some of the real problems that the quantum computing industry faces? And how can we solve them in a creative way as academics and actually have a really big impact in the field? So we're still waiting. It's been a while. But why is this? And as I mentioned, this is sort of 20 years we've had qubits, or more than 20 years we've had qubits. And there are lots of qubits around. You can see I've got a selection up here. UNSW features a lot in the different types of qubits that are out there, whether you have spin qubits defined by MOS structures, donors, superconducting qubits, ion traps, Rydberg atoms, topological qubits, photonic qubits. There are a lot of these qubits around. There are lots of simple qubit systems around where you have a few qubit gains. But why don't we have a quantum computer? Where is this thing? And why is it so hard? Well, one thing that's actually happened over the last 20 years is when this problem was posed of can you actually build a quantum computer to basically simulate nature, we didn't know how big this thing had to be. I think when I was a student here, we were talking around tens of qubits. Like maybe we could make 10 or 100, and that would be useful enough to actually solve some useful problem in the world. Turns out, the more we know, the more the more we find out, the more we actually realize we don't know about the problem. And it actually turns out to be a really, really hard one. And so this is from actually the Microsoft group in Redmond. And what their role is to work out what's the system to build to actually solve problems that you will not be able to solve on a classical computer. And it turns out, depending on the qubit parameters, like how good the qubits are, and those parameters are how big they are, how fast your clock can operate on them, and how controllable they are, you will need between several 100,000 and several million qubits to achieve what we call quantum advantage. So that's where we can solve a problem on a quantum computer where we can't solve it on a classical computer. If we now look at, actual real problems, like we will, not just get to reach quantum advantage, but to get to actually making an impact in people's lives, like things like solving problems in quantum chemistry. You hear these things thrown around that quantum computers are going to solve climate change, they're going to solve cancer, they, be used in drug discovery. If we want to get there, we've got to be in this realm of quantum chemistry. And what's the outline of these blocks? It's basically, two parameters, which are how fast you can operate the qubit, and what's its error rate. And you can see to solve quantum chemistry problems, you'll need very, very fast qubits with very low error rates, operating for months with 1 million physical qubits. And that's the best case scenario. Like, if you're talking about ion traps, which are probably one of the most advanced types of quantum computers, here we can interact with them at the microsecond level. They have fidelities around 10 to the minus 3. There are these dots out here. Well, you're going to run that same quantum chemistry algorithm. You're going to be running it for a century and need maybe 10 million physical qubits. Is that a system that's worth building? Maybe not in an ion trap system. Maybe it is, though, if you have the best types of qubits, where you're running in that algorithm for about a week, and maybe you can make 1 million. But what we're interested in doing is shifting this box down to the bottom left. So making better qubits so we can run algorithms faster and have less qubits that we actually need to make to run this computation. So making 1 million qubits. Is that hard? I don't know. Well, Apple makes billions of transistors. So this is the M2 processor. It has about 40 billion transistors on it. There's one in my laptop right here. Many of you will have them also in your laptops. They're doing that on a pretty regular basis. They've got no problem making 40 billion transistors. But why is it hard to make why is it so hard then to make 1 million? 40 billion is a lot more than 1 million. Why is it so hard to make 1 million qubits? And the big thing to realize that's different between quantum information and digital processing of information is qubits are kind of analog. And we saw from Scott's presentation before this block sphere, this state vector that's existing. Well, in reality, when we have a transistor and digital logic, we're just defining 0 and 1 all the time. And so you can be kind of anywhere on this, once you reach a threshold, it doesn't matter if you're here or here or here, anywhere around that area, you're still calling it a 1. And once you're back over this side and you're, say, gate voltage, and it doesn't really matter what you're calling a 0. So digital logic is very different to what we have to do actually to encode qubits. And so this sort of analog nature of qubits, how we construct them, means that materials kill qubits. So materials defects and the atomic nature of matter is what is so difficult about building 1 million qubits. Of course, people think they'll be able to get there. And I'm sure you'll hear a talk from SQC later on, and they will say they've solved any of these problems. But the fact that qubits interact with their environment, sort of irrespective of the type of qubit that you have. they're all susceptible largely to electrical noise, even the so-called protected topological units that I've worked on before. There are some scenarios where you are operating on them where you're subject to electrical noise. You also have magnetic noise, whether it, so electrical noise, things like charges, unbonded electrons in a dielectric are all things that are going to affect your qubit. Magnetic noise, magnetic contaminants, stray magnetic fields, and thermal noise, infrared photons coming from your fridge. They're all things which will affect your qubit and are largely linked to materials. So what I just pulled this plot from the literature. This is superconducting qubits over time and their lifetime. And you can see, all these different dots, and we've gone from 10 to the minus 3 up to sort of 10 to the 3, 6 orders of magnitude change over 20 years. That are largely due to controlling the qubit's interaction with its environment and how it interacts with the materials. So some of these are architectural changes, and some of these are real material science improvements. But there is 6 orders of magnitude change in the performance of the qubit just from how it's interacting. Yeah. You say you've got a question?
Yeah. Because I'm curious about the noise part, we have listed for the thermal or the electronic noise, but why we don't consider about the high energy particles from the outer space?
Absolutely, they are also. I guess I could have made this list much longer, but high energy particles. Once you fix all these problems, you'll still have radiation from the universe coming in. And in the case of superconducting qubits, breaking apart a particle pair and poisoning your qubit.
Yeah, I think the energy level for the high energy particles can affect on the classical bits. But why there is very less people working on this area to research about the high energy particle interaction with the qubits.
So people are. Why is not everyone doing it? Firstly, it's probably not the biggest problem in qubits right now. So when you're thinking about a problem, like you go, okay, what's the biggest thing that's limiting me right now? So I'm going to work on that. Once I fix that, I can work on the next biggest thing. So it's probably like the 4th or 5th biggest thing. But in some qubit systems, they've cleaned up all these other problems, and so they are affected by high energy particles. The other thing is it's really hard to control. And the thing about experimental physics is we like to have control of our environment and be able to turn things on and turn things off in a good way. And the way to turn off the incidence of high energy particles, galactic particles, is to dig a giant hole in the ground a few kilometers deep, and you put your quantum computer in that. And people are working on that as well. But that's a massive effort. But it's that's hard to do.
And can I have another question?
Sure.
Yeah, the last slide, in the previous slide, that figure you compare with the classical integrated circuits, right?
In terms of numbers of transistors?
Yeah, because I'm double major in the quantum engineering, so I'm curious about one thing. In our classical integrated circuits, we have the bus. It working on a very high frequency. All the signal and the classical bits will transfer their information using the bus. But in our quantum computer, like the IBM Q, I have worked on it, but there's one limitation is for the qubits connection. If one qubit is not connected with each other, I want to apply a CNOT gate. I must use the swap gates for the 2 times with another qubits. If we want to build up more than a million qubits, how can we connect it with each other? Because if I want to connect the first qubits to the...
So we'll go into that challenge. Hold on. Is that all right? There is some slides about how do you actually do this. And maybe we're even there now. And then even if we could make 1 million physical qubits, and we could test them one by one, like we had enough time, could we actually control and read them out all at once? So those algorithms that I showed, they needed 1 million qubits running all together. And that's a massive challenge. And why is that? So here's a picture of the Google quantum supremacy experiment. You can see the dilution refrigerator. Scott showed you a picture of one of the Hamilton Group dilution refrigerators before. This is one from Google where every single one of these microwave lines are coming into this bird's nest. Oops. Is carrying a signal to control or read out a qubit. And it looks a bit like sort of a telephone exchange from maybe the 1950s or 1940s, or a vacuum tube computer. Why is it like this for quantum computers, where for your Apple M2, it's got 40 billion transistors. You don't have 40 billion cables coming out of your processor, right? Yeah. And that's due to a thing called Renz's rule, which states roughly that you can get some gain in efficiency by having one block of transistors, one block of logic drive another bit of logic. And you can see here that like different types of architectures, whether like you're in RAM or microprocessor or gate array, the number of internal elements, there's a different scaling between the number of internal elements and the number of external IOs. And this is roughly, you get your 10 to the 5, 10 to the 6, or more internal elements, and it's kind of like it's still 10 IOs. And that's due to the fact that in classical logic, one transistor can drive the next transistor. Quantum computers, the line is very, very different. So here, I've drawn this point as sort of a 1-to-1. Reality of today's qubits, you're more like 10 to 1, or a couple to 1. So 10 to the 3 internal elements actually requires 3 or maybe 10 to the 4 external elements. And that's super hard. And why is this? It's due to something in quantum mechanics called the no cloning theorem. And yeah, no cloning. From your clone wars, obviously they took that from there. It's actually from a Nature paper in the 1980s, where basically they were looking at this sort of postulating whether it was possible to continuously amplify a quantum state. And just by producing more of it in order for you to detect it. And this paper shows that the linearity of quantum mechanics forbids this type of replication, and that the conclusion holds across all quantum systems. So we can't use qubits to drive qubits in the same way that we do in a classical computer architecture. And so when we go to our different types of qubits here, we have to control and read them out with physical lines coming in. And 5 wires, 10 wires. So here's 200 wires for 54 qubits, I think I took from the Google paper. The iron trap, here's a killer. 192 wires for 6 qubits. And this is sort of a Microsoft thing, so 10 wires per qubit for Mirai qubits, maybe. But there's a lot of common challenges in how to bring in a very, very high density IO structure into your quantum plane. And not all qubits are going to be perfect for solving this problem. Like, it's kind of like this Goldilocks and the 3 bears. Your qubits can't be too big, otherwise you won't fit them all on one wafer. You're going to have to run an architecture where you have sort of sub-blocks of processors that are maybe distributed within one fridge or across multiple fridges. Some people are going down this approach. Good luck to them. I think what you mentioned about sort of like a bus and the rate of information transfer over that bus. If you look at the information transfer you'll have to make in and out of 10 millikelvin environment with a quantum computer to get to the next one. You're going like sort of the optical, like many gigahertz regime. That's super hard as well. To think about running this an optical quantum bus between multiple quantum computers and multiple field bridges. Sure, and the other approach is, okay, you can go really, really small. And single donors, single electrons are pretty small. But then trying to get all these wires in, you still need a few wires per qubit. You're pushing the limits of advanced lithography. And I say that like TSMC is running a 5 nanometer node. You're going to be having to run your 5 nanometer node on the full qubit plane with 3D interconnect. That's not something. That's a technology that doesn't exist yet. So but there is this intermediate regime, where qubits may be a few microns big, with very few gates, where it might just be just right. There's also lots of different challenges on how you actually bring this thing together, and whether you're working on superconducting qubits, streaming qubits, topological qubits, your quantum computer will look kind of different, and you'll have to face these different sort of, I guess, packaging architectural challenges in a different way. But we're still waiting. Is this going to be something that's going to take the rest of my life? I certainly didn't think the progress when I was an undergraduate. I guess I sort of believed that this thing was going to be 5 or 10 years, maybe. We're like, now we're sort of 20 years further down the path. We're still waiting. We don't have. Okay, there has been amazing progress. We look at what IBM is doing now. You said you're using the system, like using a quantum computer from the cloud. That's pretty cool. But it's still not doing something that we actually really want and as society that we value. So what are we going to do? Well, what am I doing here? Like, change the focus of the story. This is a picture of my lab. It doesn't have anyone in it because I just took this photo. And Kyle, who is in my lab, is here. But we have a couple of dilution refrigerators. We're down in the basement, just down the stairs there. And we are working on technologies to try and enable quantum computing at scale. First, by looking at better qubits. So there's really, from what I said about being creative and innovative in the way to make new qubits, trying to make better materials and interact with their environment less, and new types of architectures. So different types of qubit implementations. And we're also engineering new types of quantum devices. And I think you heard a little bit in this astrophysical talk before about how photon detectors that have been able to image, millions of pixels have revolutionized astrophysics. We use the same types of detectors and technologies in quantum computing to enable sort of readout and also control at scale. So we're working on a little bit of that. The first project we're working on, because I'm really starting from the ground up with Kyle's help, we're working on trapped electrons and neon. And that's something that's really just taken off in the last year. And it's a new type of qubit where we have an electron that levitates over the surface of frozen neon. And you can see this nice rendering here. What we have is this frozen block of neon. We inject the neon as a liquid. We cool it down in a controlled manner to freeze it. And then we basically put a few hundred volts over a light globe, a tungsten filament, and some electrons fall on the surface. And if we can make some gates around, we can actually trap this electron. We can shape its wave function. And this is done by some collaborators of ours at Argonne National Lab. They've just published some nice work in Nature on this. They've actually made a charge qubit, not a spin qubit yet, but a charge qubit that is 5 orders of magnitude better than any other charge qubit made. And why is that? It's because the electron is not interacting with its environment. It's sitting up, floating on the neon. It doesn't have a semiconductor lattice around it. The neon is largely nuclear spin free and can be nuclear spin purified in the same way that silicon can. But the electron is sitting up above. And so it's a very simple, beautiful system where I'm hopeful that when we implement a spin cuban, it may be several orders of magnitude better than what's out there already. So as I said, I'm just starting out. I have a few undergraduates at the moment. I have tons of openings. If you are keen to do, come along, learn things in the lab. There is every type of project imaginable available because no one else is doing it. So you've got free pick of it. But we are doing everything: microwave engineering, designing devices, mechanical designs, building things, cryogenics, simulating devices, writing code, measuring, taking data, dealing with large data sets, doing machine learning. It's all there. And if you're interested, come chat to me. Thanks very much.
Right. Cool. Thank you very much. Right.
Hard to follow that.
But I didn't forget about it. Back to John.
All right, okay. So I thought I'd start with a little, practical demonstration. So I'm Peter Rees. You've probably seen me when I'm not flying around on a broomstick or wearing a cow onesie or like stressing over teaching. I sometimes do research. But anyway, I figured I'll do this at the start because we were missing some alcohol. And so I did a postdoc in St Andrews in the UK and we drank a lot of whiskey. So I learned how to drink whiskey. And so I figured I'd show you the right way, and then I get on with my and I'm only disrupting myself because I'll just stop after my 20 minutes. So I need some volunteers. Obviously, we only have. Sorry. Of course, yeah. And unfortunately, I only have Maya. Do you want to? No. You're okay. And I think. All right, come on. Adam, I think you were keen. Okay, you guys, come on. How many have I got? Do I need? Oh no, that's enough. All right, so unfortunately, it's like it's only Irish whiskey, but it's still single malt.
Two from UK, two from Pasteur, the cherry.
So everyone has to like take a glass.
Oh yeah. At least one.
Single malt means that it's just single malt, yeah. So it's not blended from a bunch of technologies. So grab your glass and go over there.
I'm like, shut up, you're gonna screw me.
Hold on there. Come over here. All right, yeah, that's right. All right, so line up. So okay, so the first thing. So this is a whiskey. Single malt whiskey. So, okay, so the first thing that you have to do for a single malt whiskey is you have to appreciate the color. So you have to hold up the color and you have to look at it. And if it's a light color, it might be a lighter flavor. The one thing you're not allowed to do is add water to the whiskey. You have to drink the single malt neat, sorry. Or maybe you can add a little bit of water. You have to go from the origin of, take the water from the origin of the whiskey. So you'd have to go to Ireland to get this. So we're not going to do that. So anyway, so it's a nice yellow. Sometimes they're a deeper orange color. But anyway, the next thing that you have to do is you have to kind of swirl the whiskey around and you have to look at the way the whiskey wets the glass, right? And so you can see it kind of runs down in these little tendrils, right? And so this is the legs of the whiskey. So you have to appreciate the legs. So is everyone appreciating the legs? Yes. A little swirl, yeah. Okay, and again, it's a kind of a measure of the viscosity. Okay, next you have to put your nose in the glass. Oh, yes, that's good. Yeah, so you've got to, take in all of the nice smells, the botanicals, do you get a honey smell, anything? Yeah, so obviously each whiskey is slightly different. It might be peaty, so that means it's a bit smoky. All right, so, got your nose. These aren't proper nosing glasses. But then, okay, so finally, it's time to taste. So, don't chug it down, please. And then you can kind of swirl it around in your mouth and really appreciate it. Okay. What do you think? Good? See, satisfied customers. So obviously we like to drink whiskey in my lab. Right, all right, take your glasses back. Okay, so that's okay. Notes of cherry. All right, anyway, enough silliness. Okay. Okay, and because I'm a laser physicist, I brought a laser pointer. All right, so settle down, settle down. So yeah, so today I'm just going to talk about, again, like I'm a bit of an oddity in the school. I don't do kind of solid state physics in the regular way. I'm mainly interested in optics and photonics, and I work with like people in photovoltaics and medicine, and you know, optics is very versatile. Don't have to go down to millikelvin temperatures to see interesting things. So it's quite nice. But so yes, so we work on a range of different projects. I'll just highlight a project that, you know, I'm interested in, we're working on, and again, it's something that you can kind of get involved in if you're interested. And it has a kind of a quantum-y flavor because I know there's a lot of quantum engineers kicking around. So, and I think, you know, so this is really combining optical tweezers. Hey, what's happened?
I can see it. It's reflecting back.
Oh my God, yeah, okay, that's no good. Maybe I should use the finger. Yeah, it combines optical tweezers, which is a technique where you can use lasers, high-power lasers, to manipulate, hold, you know, trap small objects. And we like to work on nanoparticles, so that's our area. And it also combines that technique with quantum sensing, right? So this is, I work in collaboration with some people at Melbourne University who do work on something called the nitrogen vacancy defect in diamond. It's not very popular up here. Obviously, we're all about silicon. But down in Melbourne, they love diamond. And, you know, this particular configuration in a kind of carbon lattice where you have you replace one carbon with a nitrogen, and then you like pull one of the carbons out, and it has a particular coordination. This has very nice, you know, properties in that it has a spin-dependent optical measurements, right? So you can basically excite, you can set spin states within the nitrogen vacancy center, and then you can read their state afterwards. And so for all the reasons why Maya said that, you know, quantum computing was challenging because it was sensitive to everything, actually makes this kind of thing very nice because actually it's like a sensor. So if you're sensitive to fluctuating magnetic fields or DC magnetic fields, it's sensitive to temperature, it's sensitive to electric field. And so, but it's very nice because it has quite exquisite precision under certain circumstances, not in my lab, but anyway. And it has very high spatial resolution. So the kind of technologies that it's competing against, you know, it has a real competitive advantage. So quantum sensing, I think, is like, you know, one of these short timescale wins for quantum technologies. Would you argue? Yeah. Okay.
Totally.
Okay. All right. Again, but anyway, so let's start with the optical tweezers part, and then I'll talk about what, you know, our progress in quantum sensing. Okay. So the first thing is about optical forces, you know, or forces generated by light. Okay. So there's kind of early concepts. So we know that electromagnetic waves carries momentum through the pointing vector. Okay. And actually, Kepler, not the satellite-y thing, but actually the dude, he noticed that as comets went around in the sky, their tail tend to point away from, you know, the sun. And he conjectured that actually that was a kind of optical radiation pressure pushing the tail away. And I think that's part of the story, but, you know, that's essentially a pretty good picture about what's going on. And so there was this notion that, you know, light could push things around, okay? And there's another kind of example called the Crookes radiometer, which was also supposed to demonstrate radiation pressure, but actually that's rubbish. It is just thermal motion, thermal convection. So the idea is that you had these weather vanes, one was painted black and one was shiny. It was in an evacuated chamber, you would illuminate it, and then it spins around. But actually it turns out that it shouldn't spin if you just illuminate from one side, but it does spin because the residual gas, you know, inside the evacuated tube is enough to kind of drive you know, you heat up the surface of the vane, and then you get a little bit of convective flow, and then the thing spins. So, Okay, but these whole ideas were around, okay? And so now actually radiation is, pressure is awfully small, but if you have no external forces, you can make it useful. So one example of something is a solar sail. And people have heard about solar sails before. So basically they're these kind of, glad wrapped thin, gigantic sheets that you attach to something, and then they're oriented such that the sun pushes against them and there's no external pressure, so they just kind of keep on accelerating. And there was the Japanese Space Agency deployed this solar sail. It was a long time ago now, 2010, called Icarus. Actually, there were a few people that tried before. Some private consortium in California tried to launch a rocket and it blew up on takeoff, so that was no good. That was $10 million of private money wasted. But this one worked. Part of the challenge is deploying it, but once it's out there, it just keeps going. And so I think they kept tracking it for a few years, and then it kind of went off the radar. But presumably, it's still.
How did it go to Venus? Just like towards sunlight? Did it like angle itself so like it like decelerates?
I think it kind of went around the sun and then followed a trajectory away from it. So yeah.
No, but how can it go towards the sun if it's sort of sail and it's like getting pushed away from the sun?
Yes, good question. Okay, that's for the astronomers, But anyway, yes, I think you can angle the thing. I don't think you can get like a kind of keel effect, but anyway. Okay, but we don't want to get distracted because that's not the important part. Okay, the important thing is radiation pressure is very small. Okay, and how small is it? Well, if you had a mirror that you were, sending light to, and you considered, okay, that each photon carried h on lambda of momentum. If you had n photons, basically they, changing direction, they'll impart that same amount of momentum onto the mirror. Okay, and it turns out that if you have a milliwatt of optical power, you generate a piconewton of optical force. Okay, that's not terribly much. Okay, so you might so those kind of force scales, right, are, actually compatible with things that go on inside of cells, like, the way motor proteins move, the way macromolecules fold up. They kind of work on this kind of piconewton, femtonewton force scale, right? So this is where lots of interesting things are, and this is where optical tweezers kind of makes its name in trying to measure these types of forces on these biological systems. Obviously, you could think, tractor beam, if you could somehow configure it, you might even be able to pick up a cow, but actually, that's not what you get. If you used a gigantic laser of sufficient power, you will probably, fry your cow and leave it as a meal. So. All right, so where did this whole notion came? So the idea about optical manipulation. So obviously, yes.
Does it fry the biological stuff, or
it doesn't
move the biological?
It doesn't. Well, technically, you're not holding on to the biological stuff, but no, you don't need nearly as much power to move a biological molecule as opposed to a cow. So I think, yeah, and it's also you work in wavelengths that aren't absorbing. So if you maybe if you had a transparent cow, you'd be okay. That would be a challenge in itself. All right, so the idea here is that, these forces are very small, very difficult to measure, and you needed the invention of the laser before you could start to push things around, really. So, okay, milliwatts, that's a laser pointer. Usually you work on hundreds of milliwatts. And so this guy, Arthur Ashkin, who won the Nobel Prize in 2018 for these ideas, he started in the 70s, and he started to kind of levitate particles against gravity. So basically push a little tiny microscopic, silica bead, glass bead, he pushed into a chamber, and then he used a laser to push it against. And so he basically levitated this against gravity. And then he came up with some ideas about, like, if I push my particle with light this way and then this way, and I balance those forces, then it becomes trapped. So this is a kind of different kind of configuration of optical tweezers. And then in 1986, he actually come up with a way of just using a high numerical aperture objective. So basically a high magnification microscope, just send a single laser beam in, and he was able to hold objects at the focus of the laser, essentially. And so again, the idea is pretty simple. If you've got your object here, it's a refracting object. basically if the light comes through and gets refracted, it changes direction. That means it has to have imparted momentum on, on the particle in the opposite direction. If you have balancing forces, then you have this thing held in the center. Okay, and actually what happens is you end up making a kind of harmonic potential, like a mass on a spring type harmonic trap. And so any motion of the particle away from that, then essentially gets it gets pulled back again. So so it's like a Hookean spring. This works in 3 dimensions, which means that it's like it's actually really quite useful. And so this is the things that we're using. Now I did chuck away a whole bunch of slides because I only have a short amount of time, and I need my demonstration. But this optical, so the optical tweezers is really where Arthur Ashkin, won his Nobel Prize for it, and it is actually used for a whole bunch of things. So you can do sensing with optical tweezers and measure displacements on, the sub-nanometer size scale. So you think, oh, optics, that's diffraction limited, right? Lambda on 2, only a few hundred nanometers. Using interferometric techniques, you can actually track the motion down to these very small scales. And this is why you can actually study motor proteins walking, along, right? So you can also apply forces, you can actuate, objects, so you can force load molecules, and see how they work under strain. And this has, relevance to, motor neuron diseases and things like that. So again, very useful. You can actually take your light and you can split it into many different spots. So now all of a sudden you can make, 10 traps or 100 traps. And now you can basically pull things around in like under your microscope and watch them interact. So, okay, so there's a whole bunch of reasons why you might want to use this. All right, so anyway. Now, so that's my very short introduction to optical tweezers. All right, and so the deal with the nitrogen vacancy, so this is a kind of classic like qubit, in some systems, but as for us, what it is it is a optical system that fluoresces, and it has a means for which I can set a spin state and read the spin state out at some later point in time. Okay, and I'll try and do a very quick, picture about what's going on. So actually, if you look at the emission spectrum, it's this defect state within the diamond lattice. So obviously it's insulated, so it has a large band gap. So this thing kind of lives in the middle. Basically what happens is if I excite this state with a green laser, so essentially I have the magnetic spin split because of the configuration of the defect. And essentially I will basically, if I excite, and I have to conserve spin here when I do this optical transition, I can either go up here and back down again. And so basically I keep cycling, and every time it drops down, it gives off a red photon and it goes back up. So this state here goes round and round, but sometimes it leaks into this singlet state and it doesn't give off a photon. So it basically tells me if I'm in the ms equals plus or minus 1 state, it will be a slightly dimmer state than if I'm in the ms equals 0 state, which only cycles backwards and forwards. It has no access or a very small amount of access to this non-radiative pathways. So basically I've got kind of 2 measurements. If my light is bright coming off the diamond, then it's in the ms equals plus or minus 1 state. And if it's in the 0, and if it's dark, it's in the plus or minus 1 state. Right, so okay, so I basically have an intensity dependence on my spin state. And if I keep cycling this over and over and over, basically all of the spins, and so these defects, I'm looking at hundreds of them, not individual ones, they all end up populating into the ms equals 0 state. So they all set into a spin state, and then basically what happens is, because this energy difference is very small, over time, if I leave it, it will kind of relax back, right? So there's plenty of thermal energy to repopulate this. Okay, or I could drive, basically apply a microwave field. So this energy gap is equivalent to 2.8 gigahertz. And I could actually, drive the spins like a Rabi type oscillation, which is what you've kind of seen before. And so I can actually manipulate the spins, and then I can read them out again with my green laser. So, okay, I'm sure I'm not doing that too much justice, but anyway, so that's the idea. So what's our idea? So we try and combine these things. So of course you can have NV, so nitrogen vacancy center defect sensors outside of optical tweezers, and they're really successful in doing some amazing things, right? You can have like really high precision, they're kind of essentially magnetometers, but they have high spatial resolution, and they have, you know, sensitivities, or that they claim that can be kind of, you know, femtotesla per root hertz type of sensitivity. So like, or, you know, very high sensitivity. Right, but what we think of them as is like little NMR machines. So basically, actually, if you can really harness the properties of these like NV centers, you can do kind of chemical mapping of very small volumes, right? And if you do normal NMR in chemistry, you actually need milliliters of, you know, of material to get a good signal. You know, need a 1 Tesla magnetic field. Or, you know, diamonds, you actually need very small fields, and you have like very high spatial resolution. So you can imagine sticking a diamond inside a cell and then doing some kind of chemical mapping inside the cell. And so this is some of the, you know, kind of reasons why people are trying to pursue this. So what we feel is that if you add tweezers to the mix, actually you can take your diamond and you can take it to places that you're interested in. And so you can move it around and map it. So I go to the mitochondria, have a look over there, and then I'll take it to the nucleus and I'll have a look here. Right, so it adds an extra dimension of control to this system. So we thought, okay, we'll grab these things. So these things are only 100 nanometers in size. We can trap them in our optical tweezers, and then we can try and do some kind of, you know, optical readout of the spin state. So that's the things that we do. Okay, so the experiment we have is kind of complicated. It ends up looking like this. You know, this is like a 3-meter optical bench with lots of optical components, and so that's the kind of thing you do if you come to my lab. Yeah, it's kind of lots of fun. Some people think it's not lots of fun. Some would argue that doing clean room lithography is also not fun. So it just depends on what your definition of fun is. But anyway, so this is a homemade microscope where we kind of enter, you know, we add in all the lasers, we add in the microwave fields, and we add in the detection system. So again, we're also using single photon counters with high precision. You know, we're making use of where the money is spent on developing the technology. Okay, so this is my little flyover view of my tweezers, but no time for that. So, okay, so, all right, so this diagram, yeah, no, it's okay. So this was our kind of, sorry, I'll just kind of skip through this stuff too much. So basically, what we're going to try and do is this technique called optically detected magnetic resonance, where we're essentially applying a microwave field. And so we spin polarize our NV centers, and then when our frequency of our RF field matches this transition here, basically things will go up into this dark state because it can relax non-radiatively, and we essentially see a dip, right? So this is our kind of signature of, you know, us measuring optically detected magnetic resonance. Okay. It turns out that actually having the trapping laser on is very bad, and it kills our ODMR. So part of our challenges over the years have been to, you know, mitigate that problem. Usually we do things like switch off the trap very briefly, do our optical measurements, or our kind of spin measurements, and then turn it back on. We can do that because we're trapping in a fluid environment, and everything's damp, and so things don't move around too much. Yes. Now we know, you know, by Zeeman splitting, we can kind of move our energy levels around. We can split the MS equals, you know, plus and minus 1 states into different states, and then we can try and measure what's going on as we apply a magnetic field. And so these are the kind of things that we do. We apply, you know, and they're not tiny fields like millitesla fields, and we'll see that the, you know, ODMR peak, the dips where we see, you know, a transition will appear at different frequencies, you know, and of course, you know, we see, yeah, basically corresponding to different energy levels. All right, and so we tried to make a simple magnetic sensor which just monitored the motion of the, you know, the peak frequency as a function of magnetic field. It's pretty terrible, but it's the first one in the trap. Another thing that we can do is if we start to apply large fields, actually, we don't have just one axis of this NV center. It has, you know, 4 different axes. So if you kind of split everything apart, because you have a magnetic field, they're kind of projected along different directions. So you have different degrees of splitting. So you end up with lots of different frequencies corresponding to these different orientations. And what we can do is actually we can kind of take our nanodiamond, and because it's slightly oddly shaped, we can rotate it with our tweezers, with our polarization. And so this causes the peaks to kind of shift around, and that can kind of tell us something about what the orientation of the diamond is in the trap, which you can't otherwise see. So this is the kind of things that we're mucking around with now. And then some other things, because we can try and make use of this kind of very small, spatial sensitivity, what we were thinking that we might do as a little demonstration is that we would split our laser into two. We'd hold a gold nanoparticle in one and a diamond in another. We know that the gold particle heats up, and so when we bring them together, we try and see whether we see a temperature shift, which then is registered in the ODMR spectrum. So, okay. And did we do it? Well, not very convincingly, but it's a hard experiment to do. But anyway, so we're working on these kind of fun things. So we're thinking about what types of stuff that we can do with our optically trapped diamond. And we're also trying to push the sensitivity limit. So we're trying to look at spin manipulation techniques that do work very nicely at low temperature, try and apply them at room temperature where you and I live. So anyway, so that's that. That's all I have to say. If you have any questions, otherwise.
All right, thank you very much. Any questions? All right. Last but not least, we have Casey Myers. You're gonna, we'll put it on the laptop.
Oh yes, you have a question?
Do you just work with elements and do you also with liquid surface?
Sorry?
Like liquids?
Can we trap liquids or do we work in liquids? So we mainly work in liquids because we're interested in biological applications. So you can trap diamonds in vacuum as well, and that's a whole different game.
You're using the diamond to measure the fields?
Yeah, essentially, we're making a small magnetometer and holding it in a laser.
Are you only to measure surfaces?
Surfaces are easier not done in a trap, but yeah, you can measure surfaces.
Can you measure something that's has a 3D structure?
You can. You can move your diamond around in 3 dimensions.
And then you have to interpret
Yeah, it would be like a reconstruct your like CT.
The rating for construction.
Oh yes, one more question, then you have to get onto this.
Observing, this is a very basic question. This is a very basic question, like observing the elements, observing the diamonds or anything. Wouldn't that affect it on an atomic level, like using light rays to measure it and to control it, right?
Oh, they're very stable. So, and we use light that is essentially it's transparent to the wavelengths that we're using. So we only experience scattering and refraction. We don't actually change the
It doesn't actually have an effect on it.
Yeah, so Kyle started with logic, and then he.
Well, it's a gray area. Yeah, it could.
But you can take account for it and you can measure how much is deviated by and take account for the
For sure, yeah. You look at the spectra and things like that. They tell you something about.
So it's like
Okay. All right. Anyway. Thank you.
All right. Thanks, guys.
Do you need glasses?
Oh, okay.
Hi, everyone. So I'll get started. So my name is Casey. I'm coming down from SQC. I'm the quantum applications and algorithms team lead for silicon quantum computing. So we're supposed to have 2 other people talk today with me from the company. Unfortunately, for travel reasons and other reasons, I couldn't make it. So I'm going to try to talk about the full stack, but I do theory, so they do some fantastic things in the lab, some fantastic magic, I would say, which really fascinates me. But I'm sort of coming from the theory side of things, so most of my stuff will be focused on that. So I liked your style of talk, so I quickly copied. No, not really. I already had this sort of thing in place. I thought I'd give you guys a bit of a tour of my background because it's a bit different to the usual academic. I didn't want it to be different at the time, but it happened to be. I'm from Brisbane originally. My undergraduate there in quantum optics / quantum computing, just as things were starting to happen in quantum computing. Had really itchy feet, had to travel for my PhD. Decided to go to a really boring town and do my PhD in Waterloo. But it just so happened to be a place where they decided to pump a lot of money in quantum computing at the time, and also theoretical physics, which was fantastic for me. Perimeter Institute for Theoretical Physics, Institute for Quantum Computing. So I spent 6 winters up there, say kind of time in Canada, and had a really good time. Wanted to come home, wanted to keep working in quantum computing, so I came back home to Brisbane to do a PhD, to do a postdoc rather. Stayed there for, I don't know, 6 odd years. Again, had a really nice time. Didn't want to leave the field, but postdocs end, contracts finish. I had a decision to make: stay in Australia, not do physics, or go overseas and keep doing physics. I decided to stay in Australia, and actually, no, sorry, I forgot to say that I sort of invented or verified time travel while I was at UT. So this was an actual popular science article that came out for some of my work while I was there. Or not really. I mean, this is a true news article, but we didn't really do time travel. Anyway, I decided to move into the, well, actually, no. What I wanted to say was before I left the quantum computing industry, things were at a certain place. Not a super exciting place. I mean, lots of fantastic things were happening, but small steps were happening. So you couldn't run anything on a quantum computer unless you were in the experimental group. They didn't have control over large numbers of qubits yet. Machine learning wasn't a thing yet in the physics community, really, or at least quantum computing. That was when I left in 2015. Went into mining for a little bit. It was really nice to see the talk before by the seismic astro. What's his term?
Astroseismology.
Astroseismology, exactly. Yeah, great. So I worked in marine subsurface seismic data analysis for a year. Actually, 18 months in Perth after my postdoc. My day was looking at this sort of data that they'd give us 10 terabytes worth of this data from below the ocean surface. Ask us to clean it up and tell them where the oil or gas was. Wasn't very much fun. So I decided to move into banking. So I moved to Melbourne, started working for National Australia Bank, where I started modelling certain types of risk for the bank. My first quarter when I was working there, I was asked to run the model, which was part of my job, to determine how much money the bank has to keep aside. The government said, keep $3 billion aside. That's just how much you have to do. You have to run a model to verify that. The first time I ran the model, I told the bank that you have to start keeping more money aside than the $3 billion that they had to keep aside for 10 years before that. They weren't very impressed. Anyway, that was more interesting work than my time in Perth, because I actually got to sort of get the code and play with the code and make modifications that I thought were worthwhile as long as I could back it up. But then I heard from a former student, a former student in one of my research groups in Canada, that they just started a startup company called Xanadu. And pretty much before he told me that, he's telling me that I could work with them, I'd already resigned from the bank. So I guess I was really keen to come back into this field. So I moved to Canada, worked for Xanadu for 18 months. Again, that was 2 winters, 2 winters too much. Decided that I just had to come home. When I did move back into quantum computing, things had changed. What was it, 3 years? In 3 years, the 3 years that I'd left, all of a sudden IBM had devices on the cloud that we could sort of log into and try to run something. Fantastic. Machine learning had sort of made its way into quantum computing, something that I didn't really know anything about at the time. And then my time at Xanadu, I was able to learn all of these different techniques that I'd sort of completely missed during my postdoc and just weren't a thing. So it was great. But like I said, I had to come home. I had to stoop to working in a computer science department at the University of Melbourne. Things you have to do to come back home to Australia. It wasn't so bad. I was working in quantum computing, which is what I really want to do, which is great. Tried to start a quantum computing group in the computer science school down there. But then I heard about silicon quantum computing, and Michelle gave me a call and said, we're looking for an algorithm person. And I'm like, great, awesome, come back to physics, keep working in quantum computing. That's great. So not many people I know of maybe 2 examples in Australia that have sort of left academia, gone into industry and then come back. So it is possible. But I just wanted to sort of go through my background because it's also worth thinking. Some students want to ask questions about what it's like in industry. So it's always good to sort of say, I've had some experience and people would have questions. Of course, I prefer academia because that's where I am. But there are positives and negatives for both. So quantum computing. So like I said at the start, this is going to be a theory-heavy talk. I'm going to try to talk about some of the experimental stuff that they do at SQC. I probably won't do it justice because that's not my expertise. I'm really interested in the algorithms that you can do on a quantum computer. What can we do to beat classical computers? That's what drives me. That's why I do this job. And one of the motivations for doing that is Moore's law, which I'm sure most of you have heard about. The number of transistors on a chip are doubling every 18 months, 24 months. So at some point, we're going to reach the quantum limit, where we're just going to have to start putting quantum mechanics into those systems to try to make them continue to work, or at least increase, keep up with Moore's law, keep increasing the number of transistors on a chip, for example. My true motivation for quantum computing comes from classic Richard Feynman quotes, which sort of say that sort of nature is quantum mechanical, so you'd better take those effects into account. And I mean, he was one of the first people to sort of think about quantum computing as a thing and something that we really need to study. So again, copying from a talk earlier, the different physical systems that are out there. So I guess, well, I don't know how many serious contenders there would be out there for quantum computing. There's at least 6, I suppose. So I've worked in optical quantum computing my time during my PhD and also at Xanadu. So I know a fair bit about how they work. And now I'm working in silicon. So there's also obviously superconducting qubits, and some of you said you've logged into the IBM quantum network and tried to run things on there. There's ion trap quantum computers, neutral atoms. There's all sorts, and there's even more types of physical systems out there, and they all have pros and cons, I guess. None of them are perfect. I want you guys to think the silicon is perfect, of course, but I mean it's not true. There are negatives for even silicon, and it's really a matter of trying to engineer the systems to take advantage of the pros as much as we can. It's going to be a marathon, not a sprint. It's not going to happen. We're not going to build a quantum computer that solves a problem that's of interest to, say, industry next year. I don't think. I'm pretty sure. It's going to be years, not just a year, before that sort of happens. But every year, very exciting things are happening in the field. And I think it's awesome that it's even an industry right now. That's sort of coming up around quantum computing. Silicon. So I'm working for silicon quantum computing. The main architecture for that company is having phosphorus doped into silicon crystals. We can use the nuclear spin or the electron spin of the phosphorus atom as a qubit, and they have all sorts of fantastic qualities, long coherence times, interesting interactions between neighboring phosphorus atoms that are doped in that silicon, if you can sort of manufacture that. In fact, that was one of the first proposals for quantum computing, I think, from UNSW, in fact, by Bruce Kane in guess, the late 90s. So silicon is really sort of tied with UNSW sort of very closely. Silicon quantum computing, we're a full stack company. Does anyone know what that means? Hasn't spoken to me before. So when I worked at Xanadu, it was also a full stack company. What that means is everything that you want to do to build your quantum device, your quantum computer, is done in-house. So you manufacture the chip, you do whatever's required to put that chip into the dilution refrigerator for silicon. You measure the results for that. You decide what algorithm to run on that system. You decide what use case you want to try to solve. So that's what it means by full stack. So I'm at the top level of the stack. So I live sort of in this region where I'm looking at applications, the quantum algorithms, trying to play with quantum error correction, but we also have some other experts that work on that as well. And then we have sort of people all the way down this list of necessary requirements to build a quantum computer. And so, like I said, we're hoping to get a couple of other people from those parts of the stack in today, but we just couldn't. But if you were to consider working on a research project with a silicon quantum computer, there's no reason why you couldn't work with people from the experimental side or the engineering side or any part of the stack, sort of the theory side. I don't really need to define qubits because two other people at least have done that for me, which is really good. So a qubit, standard definition, a bit is 0 or 1, qubit is 0 and a 1 at the same time. That's fine. Quantum circuits. So quantum circuits kind of analogies of classical computing circuits, but they have to be reversible circuits. So we're using quantum mechanics to build a quantum computer. Means everything has to be unitary, means everything has to be reversible up until the measurement stage. Not a trivial thing to map all classical algorithms over to these sorts of reversible algorithms, but people have done it. Down the bottom here, I've got an example of a quantum circuit. We have gates, single qubit gates, 2 qubit gates that interact the information carriers in our circuit. We make measurements at the end to try to read out the result. Shor's algorithm, we do some stuff in the middle, make a measurement and try to find out what the factors are of the semi-prime number. Grover's algorithm, which I'll go through in a minute, you'll do a similar sort of thing. You do some stuff in the middle, make a measurement and you predict what the answer for the problem you're trying to solve is. Yeah, okay. I'm going to go through Grover's algorithm next. I just want to give an example of an algorithm. It's pretty maths heavy. You don't have to follow the maths. What you really need to follow is what's in the red circles. This is sort of adapted from some teaching material that I had a couple of years ago. But I just wanted to go through an algorithm that's pretty well known, but it's relatively easy for a student to sort of play with this sort of algorithm and see the result. Just on a laptop. You don't even have to use any specialized quantum computing Python packages. You could just use whatever matrix multiplier you want to use, and you can sort of see this result pop out. And it's kind of fun to play with. So Grover's algorithm. So this is completely abstract. It's got I put an example just for the size of the problem. We've got some state, omega. It's some chosen state. We want to we want to find this state out of all possible other computational states that are in our system. The way you do that is you use something called oracle to give that state a phase, and then that phase tells a different part of the system that we should amplify the amplitude of that state in order to make that bigger than the rest of the state. Does that kind of make sense? So that's what Grover's algorithm does. In fact, that's what a lot of quantum algorithms do. We've got the answer in a large superposition. We want to somehow mark that superposition, mark that answer in that superposition state, and then having marked that, we can try to increase the amplitude of that particular part of that superposition and increase that to hopefully to a unit probability, and then read that out. That's quantum algorithms, I guess 101. They're not all like that, but certainly that's the way we'd like them to be. So Grover's algorithm, we've got the state Amiga. So I've given sort of abstract definitions for what the oracle and what this diffusion operator should be. Like I said, there's lots of maths here. It's not important. What's important is this part. We're marking the state that we care about. And this part here, we want to increase the amplitude a tiny bit from that marked state. That state, that part of the state now has a high probability of being measured. And so if you do that a few times, so an example here, just say we've got 8 qubits. If you do that a few times, do one iteration of this, you can see the amplitude of the marked state is 1 on 8. Okay, not exciting so far. Do it a second time. Okay, do a second iteration. That amplitude starts increasing. Do it a third iteration. That amplitude increases again. If you were to do this a square root of n times, the probability for the state will be close to 1. And if you made a measurement up here, you will have determined what that marked state was. And the first time I saw that as a grad student, I just thought, wow, that's fantastic. Like it's not complicated, and you sort of do this, and it just sort of pops out. It's fantastic. Unfortunately, this just gives a quadratic speedup. So that means that this algorithm isn't changing the complexity class of the problem. So computer scientists don't care about this because we're not really we're improving it, but it's not notable as far as they're concerned. But people in industry are certainly interested because this could save days or weeks for computations. But most people working in quantum computing are going for the holy grail of an exponential speedup, something like Shor's algorithm. Everyone's heard of Shor's algorithm, maybe. So Shor's algorithm, I'm not going to go through that today. Don't have time. I don't think. No, definitely don't. Shor's algorithm is based on something called phase estimation. I don't know, 70% of quantum algorithms are based on phase estimation. Phase estimation, we're just trying to find the eigenvalue of some unitary. If we can somehow encode our problem into this algorithm such that the eigenvalue is the answer, then we're golden. And that's how Shor's algorithm works. That's how a lot of quantum algorithms work. And this is really a fundamental algorithm for quantum computing.
Just a very quick question. Is omega an already known state or just a good guess for?
No. So in Grover's algorithm, you want to know, like you say that, I don't know, the all zero state is the marked state, for example. You have to know that because otherwise you wouldn't know how to sort of set up the oracle or the diffusion operator. Yeah. And so, I mean, this might seem like a trivial sort of thing where you're kind of using the answer to get the answer. You can use this for all sorts of things. You can use this to solve optimization problems. This is, in fact, this routine is a subset of this routine in here. That's sort of how fundamental is this amplitude amplification, which I just spoke about, sort of is hidden inside this unitary here. And it's amazing just like how often this gets used. So I wanted to mention just in the last couple of minutes what I do sort of during my day working at SQC. There's 3 steps, I guess 3 main steps to what you'd say I do on a daily basis. We in the algorithm team on the theory side of things at SQC, we want to solve difficult problems. We want to find out what problems we can solve on a quantum computer, what problems our stakeholders or customers care about solving. We want to try to map those problems to certain types of quantum algorithms. We want to extend, tailor, design. We want to use algorithms that already exist or create new algorithms to solve those problems. So it's kind of like undergraduate physics. You spend the first, I don't know, 2 years of undergraduate physics understanding the simple harmonic oscillator. And you spend the next 2 years mapping everything to a simple harmonic oscillator. Same sort of thing happens in most industries, in most fields of quantum computing, I guess. You want to try to map it to a problem we already know how to solve. The exciting part is when it doesn't map to those problems already, you actually have to do something fundamentally new. And there's both cases occurring at SQC. Once you have the quantum algorithm, we of course want to map it to silicon because silicon's going to win the race for quantum computing. And that's a fair bit of work as well. We have to sort of we have to learn what the architecture is going to be for silicon, and sort of map out algorithms down accordingly. I can see I'm at 21 minutes, so I don't want to talk for too much longer. So I might stop there. I had an example, a finance example here, but it's kind of detailed and I don't want to sort of lose people. So I'll just stop here. I just mentioned that at SQC and for most quantum computing companies and groups, there are various types of algorithms that we would like to consider. There's a standard digital algorithm which can do anything. You just have a black box and it's universal. You have some problem, you should be able to work out how to solve that problem. It's just a universal computer, effectively. That's going to take a long time to get to. I think I heard a quote earlier saying that we need at least 1 million qubits to do such a thing. So we need to be able to put error correction in there in order to protect those qubits. That's quite a way, quite some time away. There are near-term algorithms which may or may not exhibit a quantum advantage. This is a very I guess, fashionable field in quantum computing right now. If you were to look at the preprint server, there are many papers every day on this. The problem with these is it's cool to consider. It's a quantum system, it's a quantum computer, or a quantum small-scale quantum computer. You can do things on say, IBM's quantum network, but whether that leads to any payoff, it's not clear. You can also try to solve non-universal problems using a non-universal method. So you can try to hard code your problem into your quantum system somehow and try to solve it that way. And that's also another thing we're considering at SQC. We have a physical system, the silicon system at SQC. The underlying physics in that system is quite difficult to model classically. And so that's something we can try to take advantage of to run analog simulations. So sort of hard code problems into the physical system and try to solve them that way. Yeah, so I think maybe I'll stop there because I've got over to 23 minutes, but I'm really happy to answer questions. Yeah, thanks.
Any questions? All good. Just another, I think, round of applause for. Oh, sorry, Adam. Please. Do you have a favorite gate?
I do actually. So it's funny. The Toffoli gate is my favorite gate. So it's a 3-qubit gate. It's incredibly hard to work out how to do. So every time, so when I was a grad student in Canada, I had a fellow student who thought the genetic algorithm